Hello everyone, welcome to Pratibha Tech. In this video, we will solve the problem of the day question on Geeks for Geeks for 26th February 2023. The problem statement for today is number of good components. This problem is based on depth first search concept of graph. Let's now open this problem. First, we will go through the problem statement and try to understand it clearly. Here it says, given an undirected graph with V vertices, that is numbered 1 to V, and E edges, find the number of good components in the graph. So it is saying that we are given with V vertices and E edges, we need to find the number of good component. But what actually is the good component? So that is mentioned further. A component of a graph is good if and only if the component is fully connected component. In note it is given a fully connected component is a subgraph of a given graph such that there is an edge between every pair of vertices in a component. The given graph can be a disconnected graph. Consider the adjacency list from index 1. Okay, so here it is saying that a fully connected graph, a fully connected component of a graph is that portion of a subgraph, so which is actually fully connected. That means all the edges are, that means there is an edge between all the vertices in a component. So here, for example, if we take this one, so here 1, 2 and 3, these are three vertices. There is an edge between all these three vertices. So we can say that this is a fully connected component. Okay, so we have to see that how many good components are there in a graph. So here it is said that we can see there is only one component in a graph, and its component, and in this component there is a edge between any two vertices. So this satisfies the condition of fully connected component of a graph. When we look at this example 2, here it says the output is 2. That means the number of fully connected component is 2. How it is 2? We can see that there are three components in a graph. For 1 to 7, 1 to 7, there is no edge between 1 and 7. Okay, yes. So this vertices 1 and 7, these are not connected. So there is no edge between these ones. So that's why it is not a fully connected component. Rest two are individually fully connected component. So yes, this one there is a edge between any two vertices, and this 6 is individual ones. So it is having only one vertex. So there is no point in getting connected to itself. So this can also be considered as a fully connected component. So how we will actually find the number of connected components in this one? For this one, we will follow the approach of depth first search. So what we will do, we will start from one node and we will try to see. That means we'll try to see that all the edges connected to it. That means all the vertices connected to the node 1. Here we can see it is connected 3 and 2. So for each of the neighbors, that means we can consider that 3 and 2 are the neighbors of node 1. So we will go to each of them at once, and we will again try to find that what are the edges or the neighbors of that particular component. If at any given point, if you find the degree of a node is same for all the vertices, then we can say that it is a fully connected component. So here if you can see that for 1, 2 edges are component. For 2 also 2 edges are connected. For 3 also 3 2 edges are connected. So there are 3 vertices and 2 edges are there in each of these nodes. So to connect one node to other two node, we need only 2 edges. So that's why we can consider that this is fully connected component. So here see here we have been not given the input format, that how the input format will be. Okay, so we will understand it in a little better way by just going through the custom input. That means how the input will be given, that how to proceed with this adjacency variable here. For that we'll click on this custom input. Here it says just a minute. So input format is the first line should contain E and V. Each of next E lines should contain two separated integers. Okay, so here it is saying that E and V, then this means first line is E and V. E means the number of edges and V is the number of vertices, and each of next E lines should contain two space separate integers. So here we can see that in next E lines, that means the next E lines will indicate the edge, that means which two vertices are connected. Here we can see that this 1 and 2 indicates node 1 and node 2 is connected. It's saying that 1 and 3 is connected, and this is saying that 1 and 4 is connected. Okay, so from 1, 2 is also connected, 3 is also connected, 4 is also connected. So each of next E lines will indicate the edge which is connected to two different vertices. And here it is saying that a total number of vertices are 4. So one is connected to 2, one is connected to 3, one is connected to 4. So these are the thing. If you look at this example, and if you try to understand it, this one, that it is saying that 3 edges are there, that is 1 to 3, 3 to 4 and 1 to 4, and 4 vertices are there. So let's try to understand it with an example, saying we'll just try to draw this. Let's go to canvas, Chrome app. Okay, so here it is saying, let me just see if I can copy it there. Am I able to copy? No, not exactly. Something else is required, that I'll figure out later. Yeah, so from here you can see the 3 edges are there. So let's draw four vertices are there. So 1, 2, 3, 4. So these are the 4 vertices given in this example. So one edge is there between 1 and 3. 1 and 3. So let's draw one edge between 1 and 3. So then we have an edge between 3 and 4. Edge between 3 and 4. Okay. Then we have one edge between 1 and 4. So edge is between 1 and 4 as well. So that's it. None of the vertices is connected to 2. So this is the input here. So if we compare this one with that example it was given, so this is a fully connected component and this is an individual component. So here the output will be 2. Okay, so here 1 is connected to 3, 3 is connected to 4, and 4 is connected to 1. None of the vertices is connected to 2. I hope this is clear. So we are drawing this way only. So this way we are passing the input. So yeah, but we are getting here adjacency list. Let's try to print it and see that what exactly we are getting here in the input. See, this we are doing to understand the input format correctly. System.order println adj. Okay, this requires some return also, so simply return 0 for now. This will definitely be a wrong answer, but yeah, just to understand the input more correctly. So see here it is saying that, see, this adjacency list, whatever we are getting, this is in this format. So here now let me extract it somewhere so I can be on both the screens simultaneously. Yeah, so here we can see that okay, so this adjacency list is a array list of integers. So for the first one, it is starting with index position 0, and there is we have to start with index position 1, that means node 1. That's why there is no connected node, that is fine. So here we can see for node 1, that means at position 1 in this array list, 3 and 4 are connected. So from this node 1, 3 and 4 are connected. So 1 to 3 and 1 to 4. From node 2, it is not connected. Node 2 is not connected to any of the vertices. So that's why it is blank. 3 is connected to 1 and 4. 3 is connected to 1 and 4. And 4 is connected to 3. 4 is connected to 3 and 1. So if you look at this, that means this output format here, that means this adjacency list here, whatever we have got just by printing it, and we compare it with this input. Where is that gone? If we compare with this input, then we can see both are same thing. Let me minimize it. So if we can see this, not this one definitely. Sorry, I'm just facing some issue with operating with this, not required. So canvas is here. Okay, yeah. So if you compare both this input, so 1 to 3, that means here either we can consider this way, this adjacency list, that 1 is connected to 3 and 1 is connected to 4, 3 is connected to 1 and 3 is connected to 4, 4 is connected to 3 and 4 is connected to 1, or we can either go through this adjacency list or through this edges, that there is edge between 1 and 3, edge between 3 and 4, and edge between 1 and 4. So both are same thing only. So here what we will try to do, so we will try to go to each of the node and just see if it is not visited, then we will mark that visited, and we will try to see how many degrees what is the degree of that particular node, that means how many edges are there. So if you can see if once that we find that, then we go to each of each neighbor and try to find the same degree there. And if you see that all the nodes are having same degree, then we can see that all the graphs are fully connected. But if at any place we find the degree is not matching, then we will simply return the negative scenario from there, that it will be 0 or that count. We will simply not include that one. I hope this much is clear. So now let's start coding for this solution. I'll be explaining it more when I will be coding it. So I'll just delete this part which I had written just to understand that input. So here what we'll do, here we'll start, here first we will create a boolean visited array, new boolean, and it will be from v plus 1. So it will go to up to all the vertices there. So we are marking that one. So we are creating this boolean variable to store with this name visited, to store all the nodes that have been visited at any point of time. Okay. So after that we'll start with our iteration, saying for loop int I is equal to 1, then I less than equal to v, sorry, v is capital here, okay, and then I plus plus. Then we will see if the node I is visited or not. So if node I visited of I, if it is false, that means if it is not visited, see, if it is visited, then we have already taken care for that node, so then it is not required to proceed further for that particular node. Then if it is not visited, then we will say that if it is not fully visited, okay, so here we will create a one variable here saying that total nodes, that means total degree from that vertex. So for that I'm creating a simple variable calling total nodes is equal to 0, initializing it with 0, and I'm marking, I'm marking initializing that this is fully connected for that particular node as true, connected as true, And if any given point I find that if it is that it is not it is not satisfying the condition of fully connected, so that time we can set it as a false. So initially we are marking it as a true, then we'll check for the negative scenarios. I hope this is clear. Now first let's define these two variables. So I'll be using this one in the method below also. So that's why let me create it as a global variable. Let me static, else I have to pass to that method, and that will simply increase the number of parameters that is getting passed. So to avoid that one, let's create it as a global variable saying total nodes is equal to 0 and static boolean is fully connected is equal to true. So initially we are keeping it as true. Then what we'll do here what we'll do, we will get adjacency from this adjacency array list adj dot get I. So get of I dot size of so what it will return, see here we are starting with 1, so adj dot get 1, so that means it will fetch this one. So and we are checking that what is the size for this one, the size is 2. That means from this node, that means node 1 I is equal to node 1, I is equal to 1, from node 1 two vertices are connected, that means its degree is 2. So we'll simply store it in some variable called degree. Okay, so it is 2 here. Now for that particular node we will do a depth first search operation. That means we will try to check for all other nodes as well, that means all the neighbor nodes of that particular node I. So for that one, what we'll do, we'll call a method dfs of I, then we are passing that degree there, then we'll pass that visited boolean array, then we'll pass this adj. So for each of these each of these values we are passing the node, the degree and visited and all these things. And once this is done, then some manipulations will happen in this method that I'll show in some time. Then after that we'll check, is the value of is fully connected still true? Initially we have set it to true. So if it is still true, that means all the conditions satisfied even in this DFS method, none of the condition broke. So if it is still true and total nodes minus 1 is equal to degree. See, this total nodes minus 1 is equal to degrees. How many nodes are there in the question? If you see, then 4. That means 4 vertices are there. So 4 minus 1. Okay. So the number of degree of this one and total nodes whatever we get. That means not 4. That means the nodes which are connected in a subgraph. That means the component which we are taking into reference. If in that component, so here we can see 1 is connected to 3, the example which we have seen here with that canvas. Yeah. So in this one was connected to 3 and 4. So these 3 vertices were connected. So if you see to this one, the degree of each of these will be 3. So how many nodes are connected? 3. So that total nodes minus 1 should be equal to degree. So that's why total nodes minus 1. That means for connecting one edge, for one edge 2 nodes are required. So that is the same thing here. So if you are having 3 nodes, then a degree will be 2. So 3 minus 1, that 2 is equal to degree. Then what we can say, then we can add it to a count which is saying that this is a fully connected component. So for that we will count plus. Okay, but we need to even define this count variable. Int count is equal to 0 initially. So if it is still fully connected and total nodes in that particular component -1, if that is equal to the degree, then we can say that yes, we have got one fully connected component. Okay, so now we have to this method is getting closed here. So now we have to create this DFS method. So just to save some time, I have already typed it. I'll just copy it here and paste it, but I'll explain it here. So once we are going to this DFS method, so what we are doing, so for the node, for each node in reference, we are marking that node as visited. Then that we are adding that yes, that node is plus, that means the total number of count is incrementing by 1. So whenever we are visiting the first node here, where is that canvas? Let me just merge it here. Okay, yes, I merged it here. Okay, so here if we are at this point, if we are at 1 here, then we will first mark that visited of 1 is equal to true. Then total node, it was 0 earlier, so now it will become 1. Then here we are checking that the size which we are passing here, that was the degree here, degree. So that is so if it is not equal to adj dot get node of size. So here what we have passed, 1. So from this adjacency list we can see the size of 1 is 2. That means 2 integers are there, so the size is 2. So if both are not matching, then only we will mark it as a false. But here size is also 2, but and from this one also we are getting the size 2 here. So this value won't be updated, it will still be true. So after that, what we will do, we will try to get all the neighboring nodes of that current node. So for 1 it was connected to 3 and 4, as we have seen there. For 1 it was connected to 3 and 4. So it will take one edge at a time, one neighbor at a time, and we will see if that node is still not visited. If the neighboring node is still not visited, then we will perform the same operation of depth first search for that particular node. That means from 1 we saw that 3 is connected and 3 is still not visited. That means the visited array for that particular node, that is still false. So we will perform the same operation what we have done here for 3. So after this is done, then we will perform that for if 3 is connected with any other node. So we will perform that for a neighbor of 3. If not, then it will come back and check for the another neighbor of 1. So that we will perform the each operation, and we will see that is the degree at any particular node is matching with that current node in reference. So if you can see 1 is connected to 3 and 4. If you go to 3, then 3 is connected to 1 and 4. If you go to 4, 4 is connected to 3 and 1. So here we are getting that all the nodes are having same number of degree. So it will just keep updating the same thing, and total number of here nodes will be 3. And for that only we will check the total number of nodes minus 1 should be equal to degree here, that will be equal to. I hope this is clear. So I'm done with my coding. So let's try compiling this code. Something total nodes cannot find symbol. Total nodes, line number 45. Oh, I think, see this one, the spelling is not correct. Total nodes. Okay, let's try again. Again some problem is there. Line number 47. dj dot get of I. Oh, sorry, it has to be get function is there, so it has to be with a smaller bracket, not with that square bracket. Missing. Okay, here we have not returned this count variable. We need to return this count variable here. return count. So here we can see we have got our output correctly. That means we have got two components there. So if you see in this example, so one is this good component and another one is 2. Since 2 is having only this component, that means this component includes only one vertex, so it is, we can consider it as fully connected, because there is there need not be there any node or any other edge between any other vertex, because that component consists of only one vertex. So this is done. So let's check for the other example also. So here you can see, if you try to draw the same thing here for this one, then what we can see, one is connected to 2, one is connected to 3, one is connected to 4. So let's delete this one, then we'll try to, so here we'll draw 1, 2, 3, 4. So here it is saying one is connected to 2, one is connected to 3, one is connected to 4. So one is connected to 2, one is connected to 3, one is connected to 4. So here you can see one is connected to 2, 3 and 4 according to this question, this input here. But there is no edge between 3 and 4, there is no edge between 2 and 4, there is, so these two things are missing. That's why this cannot be considered as a fully connected component. So here for this, the output should be 0. So we have copied this. Let's try compiling this code. So see, here we have got our output as 0 only. So now let's try submitting the solution. So here we can see that we have got all the test cases passed and we have solved this problem successfully. So I'll be providing the link of this question in the description box, so kindly check that. That's all in this video. Please like, comment and share the video, and please subscribe to the channel for more upcoming videos. Thank you for watching.